when Tony, like before his talk, he was talking about how he lives in Brisbane and what he does and so on. So I live in San Jose. So basically the ocean is kind of close. So like twice a month we drive to the ocean and walk along the beach. Otherwise I ride my bicycle in the time free from like having fun. I go to work to Salesforce, where I am data engineer or something. And at night I teach in Santa Clara University, teach logic and formal methods.
Have you visited the new Salesforce Tower in Bryant Park?
We're not allowed. No? Like our badges wouldn't work there yet. So some people go there, but it's not easy to penetrate. So, and I work in Palo Alto anyway, so our office is in Palo Alto. So the advantage is like you don't have to drive to commute there. Like riding on a train, reading books, cool. Okay, so hi, you see my name. I've been talking at this conference like for 3 years or 4, something like that. So this talk is probably the easiest, like no deep math, no like deep programming. It's just more like to dispel the, like the idea that people get from their teachers, I don't know since when, like since the beginning of 20th century or since the beginning of this like our era, so I don't know. So the things have changed. The changes didn't penetrate the brains of teachers yet. It's like number 0. So if you go to school, you learn that to count from number 1. Why? Because ancient Greeks didn't recognize zeros. Ancient Indians did, ancient Greeks didn't. So it's still there. So the same with theories. So as a programmer, you encounter this thing like from time to time. So expression problem. We have some like interfaces defining like this and this and this, and we have to do this and this and like add more functionality. So what are the things that we are talking about? I'll try to express it from pure mathematical logical point of view. So here, so the idea is that the things we are talking about are theories and model. So what's a theory? A theory consists of types. Basically, there could be just one type. I don't know if it's possible to have 0 types, probably if it's an empty theory. So, but if you have types, there are also operations. Operations have 2 kinds. One is a function. A function has a list of argument types, has a list of arguments having like different types, or maybe the same types, and a result type. So it's a signature of a function. And relations. Relations have a list of argument types, but since if we don't involve Boolean type or logical type, because not every logic is Boolean, so then we talk about relations as just something that has a signature with argument types and no results. In addition, we can have axioms. So axioms, there are expressions, first order language expressions. What's first order? Functional expressions, relational expressions, variables, also logical connectives, and quantifiers. Quantifiers meaning universal quantifier and existential quantifier. So any such an expression, if it's a well-formed first order expression, can be used as an axiom in the language, in the theory. So here's an example, monoid. Everybody knows what a monoid is. So there's just one type. Well, if we talk about like a monoid of strings, so that's not a theory. So this is a theory. So we have a type. We have 2 operations. One is nullary, so z, neutral value, and one binary operation. These are operations. They allow us to create expressions. But there are also axioms. So see, this is a first order expression. Quantifier, universal quantifier, 3 bound variables, A, B, C, and this equality. Like if we do this operation on B and C and apply operation to A, with that result, it's equal to this. Another one is for nullary sorry, for the neutral element, operation is, well, it's neutral for that operation. So that's how it is. We don't say what is it, like what's the nature of our monoid. We only talk about the language and a couple of rules. Yeah?
I have two related questions. First of all, are axioms required to be entirely first order? And secondly, can quantifiers, universal and existential, occur anywhere within an axiom, like a predicate statement?
Yeah, they can. So basically, see, it's not like the common general, absolutely like generic theory of theories. This is more or less specific. Like it's a theory. I'm talking about theories that are described using first order axioms. There can be other theories. So like, well, you can say these are first order theories. So it's not like a totally general. So yeah, you can talk about like generalize over probably axioms or types, whatever. Yeah.
So is this notion of theory powerful enough to capture the notion of a field?
About what?
A field.
I don't know
So
what.
on the,
Oh yeah.
subtract, multiply, divide by anything.
Yeah. Fields. Yeah, fields can be covered by that. Yeah.
Because the Lawvere theories are only.
Well, in this one, no. I'll go further and explain the difference, like how come fields have this have these specifics and things like this have like a different features. Yeah. So this is just an example of a theory where we have our axioms defined in a pretty simple way. Another kind of theory is like this: partial order. So the same case where just one type, just one operation. I denote it like for the purpose of like being over formal as LT. Of course, you could just write like less than and have it infix. And a couple of axioms, like for every A and B, if A is less than B and B is less than C, then A is equal to B. And this is a logical connective. And the other axiom is transitivity. This is what, like reflexivity? No, antisymmetry. So these two axioms define partial order.
Do you need reflexivity? Do you need
It's not reflexivity, no, it's antisymmetry, that's what it is, yeah.
Okay, but don't you need another axiom for all A, LT, A, comma A?
Well, this is a strict order, LT, so.
Oh.
Yeah, so like another version of partial order is where you have non-strict order, then like it's either equal or less than. So this is a special case, a theory of strict partial order. So we have A is strictly less than B, and B is strictly. Oh, what's that? Oh, I was totally wrong. Sorry.
So
No, less or equal. That's what I meant. Yeah. Yeah. Sorry. I was totally confusing everybody. Yes, of course. It's regular partial order with non-strict. So if A is less or equal to B and B is less or equal to A, then A is equal to B. That's what it is.
okay, but it could be that nothing is less than or equal to anything else, according to this, right?
Could be.
How about the reflexive axiom? Yeah, that's what A is less than or equal to.
Yeah, should be there. Yeah.
It's a minor thing. Don't worry.
Yeah. Let's go to like an even bigger theory where we have three types: points, lines, circles, and it's a segment of Euclidean geometry. Euclidean geometry, the classical geometry, contains these three kinds, like points, lines, and circles, and tons of operations and axioms. So operations are like point equal to point, line equal to line, circle equal to circle. There's no equality defined for points and between points and circles. Between point A is between point B and point C. Well, of course, it's only applicable to points that belong to the same line, but that's a different story. So this is just a relational symbol. Is on means that point A is on line B. Point A is on circle C, and this is a functional signature. Center of circle C. P is the center of circle C. So So we have mostly relations except this for this one. And we have tons of axioms. Continuity axiom. For every 2 points P, P is a point, Q is a point, and P is not equal to Q. I don't know how come it's not like rendered properly. There's a point between them. So that's from the axiomatics, Euclidean axiomatics. Line can be defined by 2 points. For every 2 points, there's a line such that point P is on line A and point Q is on line A. If 2 points are not the same, and P is on line A and B is on line P is on line B, and P, Q, yeah, 2 lines B and A, and they are not equal, so these 2 lines are equal. So, and there are tons of such axioms. I'm not going to list all of them. It's a big theory. So we encountered equality here and there. Equality is also a kind of is a relational symbol. So a theory is called equational, and the relation is called is denoted as EQ, or denoted like this. If it has this equivalence relation, A equals to B. An equivalence relation just means that A equals to A, it's symmetric and it's transitive. So when our theory had this feature, it's called equational theory. Another example, piano arithmetic. We have just one type. We have 2 operations. One is nullary, 0, and another is unary, next. And we have equality. And we have 2 axioms, or maybe more. Like next is not 0, and if next of A equals to next of B, then A equals to B. Probably there could be more axioms. I didn't go deeper, or maybe that's enough. So just another example of a theory. Set theory is also just a theory. So it's an equational theory that had these types, sets, and just one relation, this. Well, and another relation, equality, right? And we have axioms. Well, you know, axioms can be different in different set theories. If we talk about ZFC, Zermelo-Frenkel with choice axiom. So we have this set equality. If two sets are equal, if and only if they both contain the same elements. Empty set axiom. There's an empty set. There's a set that that contains no element. Union axiom, and there are more. Yeah.
So, in what reason in this context is union not an operation?
Well, see, if you look into Zermelo-Frenkel axiomatics, you cannot build union out of how they call it, separation axiom, right? Because you can try to wow. Okay, here. You can try to define like A union B equals the set of such X that X belongs to A, or X belongs to B, right? But by axiomatics, you have to write something here. And to define union, we don't have anything until we have a union. So that's how it is. That's why we need it.
I mean, we're allowed to reference or too. I mean, that disjunction.
Or is okay, yeah. Disjunction, yeah, but.
I mean, it had to come from somewhere. It came from the underlying. This is like ambient language.
Well, there should be something that that for which A and B is like a subset of that something.
So or comes from the subobject classifier. You've got the 2-point set, and all subsets can be represented as maps into that 2-point set. And so then all of the functions between products of 2-point sets and the 2-point set give you your logical operations.
Yeah, if you look at it like from general like topos logic, yeah. But here is just first order logic, so we use connectives and we don't like assign much of a meaning to that, to this. So that's why union axiom is suddenly required.
Yeah. Not defined as an operation. Defined.
Yeah, you cannot like define it through other things. In Zermelo-Frankel, maybe in other set theories it can be defined. So category theory is also just a theory. So two types of, we have object and we have arrows. Operations, D0 from arrows to objects, domain. Codomain operation from arrows to objects. And we have composition, which is not functional, because not every two arrows can be composed. And we have a bunch of axioms defining these things. So these are examples of theories and like more primitive, very small examples that could be used to talk about things like 3 values or more. A theory of 3 values. So just one type, no operations. Well, and it's an equational theory, so we have this one signature for equation. And one axiom. There are 3 elements, A, B, C, such that A is not equal to B, and A is not equal to C, and B is not equal to C. That's it. So what's that like? What's the nature of these elements? Nothing. Just we say that they exist. So this is a theory, well, because we have types. We have 0 operations, except equation, and we have one axiom. Theory with one more axiom. We take this theory and add one more requirement. So first, there are 3 distinct elements, and also there's nothing more. Like if we take 4 elements, and A is not A, B, and C are distinct, then D would be one of them. So this is the theory of exactly 3 elements. That's it. So it's pretty primitive, right? But it's like, it's a good thing to experiment with to see. Yeah, you were having a question. No. And a theory is called free. It's also known as the first order language because the expressions we had were first order. If there are no axioms, like a language of algebraic expressions, if we build something like a monoid, right? So we can put parentheses and we can put this operation, and we don't do any actual operation, like we don't define what is equal to what. So basically what we have is a binary tree. And no axioms about it. So that would be a free theory. No axioms. A theorem in theory is any expression that can be deduced from its axioms. What does it mean deduce? Well, probably we have to use some like deduction theory, basically just some logic. For example, in monoids, we can prove this just from definitions. For every x, if for every y, x of y is equal to y, then x is a neutral element. We can prove it. I'm not going to prove it, but that's something that follows from the axioms. A complete theory. A theory is called complete if every statement, first order statement, can be proved either true or false. Here's an example, counter example, piano. One would like, a while ago people were thinking probably we can prove anything about numbers. Then Gödel showed that no, and there are like pretty cheap examples, Goodstein sequence. Everybody knows about Goodstein sequence? Nobody knows? Goodstein sequence is like this. Take a number, like in this case 19. Represent it as a tower of, oh my god, not this one. Tower of 2, so it will be like 2 to the power of 2 to the power of 2 plus 2 to the power of 2, right? No, plus 2 plus 1, right? So that's step 0. Step 1, replace 2's with 3's everywhere. So we'll have 3, 3, 3, plus 3 plus 1. And like 1a. And step B, just subtract 1. So we'll have 3 to the power of 3 plus 3, which is what? Yes, so, the power of 3, right? So Wikipedia says that this is the number. Plus 3? Oh no, plus 2, should be 2.
Why wasn't that one substituted?
Why what?
You replaced all 2's with 3's, but that one you didn't replace with.
It should have been 3, yeah. It should have been 3, so I made a mistake, yeah. Yeah, it should be. Right. Okay, so
The new
Yes,
number
it
is
is three. That's correct.
it should be 3, yeah, so it was a mistake. So next we will replace 3's with 4's and subtract 1. So you see it grows extremely fast. But what we do, the tower eventually, well, because we deplete these smaller things, so we'll have to subtract 1 from this bigger tower. So the higher level number decreases, so it will be 2, and it will not grow anymore. So eventually, we'll get a 0. We cannot prove it using piano axiomatics. We can prove it like with an extension, introduce some axiomatics about sets of numbers. So in Wikipedia, you can, in the article about Goodstein sequence, you can see that the proof is pretty simple, but you need set theory, for instance. In set theory, it's easily provable. Well, and it's like intuitively obvious, but what is intuitively obvious to us is not provable in piano arithmetic. So it's like a visible example that piano doesn't exactly describe all possible properties of numbers. And there are other theories that are not complete. Geometry. Well, geometry includes piano numbers, right? Well, because you can build integer numbers in geometry. Set theory. Well, we all know this. First, like it contains numbers. Then, like continuing hypothesis, everybody knows it can be added. So it can be proven or disproven. So how about the theory of at most 3 elements? Is it complete? No, because it can contain 3 elements. It can contain 43 elements. It's not complete. We cannot like say that we know everything about it. But the theory of exactly 3 elements, it's complete. Yeah?
So isn't Euclidean geometry in the sense of whether a point is constructible or not complete?
No, I'm just talking I'm just saying that piano arithmetics is a part of geometry. Well, you can build, you can model numbers, integer numbers in that geometry, which means all the things in integer numbers can be modeled. So, like, we'll have Goodstein problem again there. This continuity axiom probably wouldn't help. I wouldn't say I know, but probably wouldn't help. So that's like a kind of cheap, vague reason why it's not complete. Well, because it includes piano numbers, so Gödel theorem applies. So now, yeah?
Does this depend on your choice of semantics?
There's no semantics.
Yeah, okay.
Semantics, we only know axioms. Like semantics is where like we try to interpret it somewhere. We don't interpret, we only see axioms and we try to prove or disprove something based on the axioms.
Right.
But semantics may help. Like you can build like an example where it doesn't work, so okay, yeah. To disprove, definitely. It's like testing. So, 2 kinds of theories. A simpler kind is called algebraic theory. It has types, it has only functions and as operations and equations as axioms. So, for instance, like no complex, like complicated axioms, just equations. So monoids are an algebraic theory because what? Because we have functions and we have equation like this is equal to this, like two axioms actually. One about the neutral element and the other is for associativity. So that's algebraic. So neither set theory, nor like 3 or more elements, nor geometry, nor piano are algebraic theories. Why piano is not an algebraic theory? We have only functional element, right? See, let's look at piano arithmetic. It's not equation that we have. So the axioms don't look like equations. Don't look like something a equals like x equals to y. So that's why it's not an algebraic theory. Geometric theory. People use the term geometric theory by denoting like a general idea of theory. So every theory is geometric. Some of them are algebraic. So it's not like separation. So geometry is geometric theory. Piano is geometric theory. Sets is geometric. And like regarding categories, so there are tricks where you can represent a geometric theory as algebraic. But it's like it's a little bit different theory. Now it was theories, right? Models. A model is a representation of a theory A in theory B. Like we can represent piano arithmetic in Euclidean geometry. How? We take a line and 2 distinct points on it. Well, we know the axiomatics tell that 2 distinct points exist on a line. Then use that segment as a unit. What does it mean? Like segment is not a part of the language, right? But we can talk about just points. Then using circle, so we have a line, find 2 points, and one of the axioms said that there is a circle with a center here, that this point is on that circle. So we do this, and the other axiom says that there is an intersection. So we can say like 0, 1, 2, and build these things forever and model piano like this. That's how probably like they teach in some schools at school. So you can build this, and you can prove using Euclidean axioms that piano axioms are satisfied here if you build it like this. It takes time, but well, it's doable. And well, yeah.
So there's a free theory where you have 0 and successor and no axioms.
Yeah.
Is the free model of that a model of piano arithmetic?
Well, yeah, interesting. Well, see, for that, you can also model it like this on a circle. 0, yes. And then they like get back, but because of this.
That's not a free model of the...
I'm not talking about free model. You said that take a free theory, which is where we have like...
Take the free theory and then take the free model of that on set.
I didn't talk about free models.
Okay, not yet.
Yeah. Yeah, free model is a different story. I don't believe I cover it. Yeah. Free model, or is it the same as universal model? No, I'm not talking about that. So it's, yeah.
Yeah, one question is, are we using classical logic or?
Yeah.
Yeah, okay.
Yeah. So I'm not going, well, basically, we don't need classical logic. Like nowhere, if you prove something, yeah, you can prove something in classical logic, but that you cannot prove in like intuitionism, for instance. Or I don't know, probably in linear logic, I don't know. But it varies, and I believe it's just a different dimension. Like which logic we apply. So in geometry, because of geometry, because it's 2-dimensional, so we can introduce rational numbers, just like split these things, and it can introduce square roots, but not cubic roots. We can also extend that piano for that, but anyway, no, we cannot. So in a narrow sense, that was a model like in general sense. A model means representing one theory in another so that all axioms are satisfied. So that you can show something, if something is not satisfied in your model, it means that, well, it cannot be satisfied over there in the original theory. But there is also a popular narrow sense of a model of your theory in set theory. So here are like two specific examples of how we model algebraic theory and geometric theory. An algebraic theory, a model of an algebraic theory T in a set theory. Set theory. Pay attention to this. I'm not specifying any like specific set theory. So it consists of mapping of types to certain sets. So each type maps to a set, like type A maps to set M of A. And mapping functional symbols. If we have a functional symbol with this signature A1, A2, and so on, AN, to be, so we'll have a for every such functional symbol, we'll have a function M of A by M of B, and so on. So we simulate our theory in sets. It doesn't. When we talk about like group theory, for instance, people say a group is a set. No. A set is a model of group theory. A group as a set is a model of set theory. You can model it like anywhere, in a general sense. So these mappings, well, to be a model, they should satisfy the equation. Hello, in the theory. So what we had in the original theory should be valid here. Here is an example, like monoid theory. So it's an algebraic theory, so what would be its model? A set with neutral element and with an operation from x cross x to x. And they should satisfy this. So that's what like you encounter in life. On the other hand, you can also say like, oh, I model a monoid in my like types. I model a monoid in my code. So just have this whatever. Maybe it's not a set, maybe it's a list, I don't know, like in your code. Some languages don't have sets, like JavaScript doesn't have sets. Can you have a monoid in JavaScript? Yeah, kind of. So it's doable. So this is an example of a model of an algebraic theory. For a geometric theory, what we need is this. We map types to sets again. We map functional symbols to functions. And also relational symbols, like if we have a relational symbol of signature A1, AN, we'll map it to n-ary relations on this M of A cross M of A2 and so on. So basically defining a subset of this Cartesian product. So that's how you model it in set theory. And all these things should satisfy the axiom that we had before. So like, for instance, field theory, not in physical sense, in the sense of like how you define a field in math. Like, what's that? Like a ring where almost everything is invertible. So, except zero. So you can define all those axioms, and as field as a set would be something that has all these operations, like inverse, or you can either define inverse, or you can say that like for every x and y, where for every x there's a if x is not 0, there's a y that x multiplied by y is equal to 1. So that's like one of the axioms of field. So example of models of geometric theory, like the theory of partial orders is geometric. What is its model in sets? Any partially ordered set. So that's where this set is coming from its models. So, and it should satisfy the axioms antisymmetry and transitivity. Antisymmetry or lax transitivity, antisymmetry. So what's a model of category theory, right? So can we have a model of category theory? Only small categories can be modeled in sets, right? Because like by definition of model in sets, we have to have sets. So okay, it's doable, but we also are pretty much aware that there are more like categories that we like can embed in sets. So how is it? But then we can start not with category theory, we can start. So yeah, before that, like I'll go further there. Probably it's not. It's a misplaced slide. So, expression problem, like expressed from this point of view, is this: we have a theory, the signatures and features and whatever, and all these things like eval, view, and so on. They're models of that theory. So that's what you do when you like implement these things. Interface is some kind of theory, and these implementations are models. So another counterexample, like of a model, take set theory. It's a geometric theory. What's its model? Where's the model? You cannot like model set theory in set theory, right? So what do? We need another set theory. Newman, Bernays, Gödel set theory will work for modeling Zermelo-Fraenkel set theory. Well, because it has like classes, so you can embed the whole Zermelo-Fraenkel set theory into this set theory, and it's okay. But how? Yeah.
I'm sorry, I'm missing how we called like poset and set like geometric theory.
Ah, see. Let's go. Good question. See why it's geometric? It doesn't axioms don't consist of, well, first, the relation is not a functional symbol, right? Also, the axioms don't consist of equations. That's why it's geometric. So like some views are that like if it's multi-sorted, so it's geometric, and if it's single-sorted, so it's algebraic. Actually, multi-sorted algebraic theory are all around. Okay, I'm not like coming up with examples, but anyway, yeah.
Graphs.
Yeah.
So you've got a sort for vertices and a sort for edges.
Yeah, and a map from like edges to vertices. That's it, right.
Because equational means algebraic and non-equational means non-algebraic, which
Yeah,
means
yeah,
geometric.
yeah. So, but then like, are there turtles all the way down there? How do we model NBG? Well, for that, Grothendieck came up with a solution. It's not set theory, it's like a small segment consisting of the axiom that we really need. So it's called Grothendieck universe. Mathematicians are still basing everything on sets on models in sets, not even mentioning like what kind of set theory they mean. Probably Zermelo-Fraenkel is enough. I don't know. I'm not a mathematician. But if you go deeper, like how do we talk about theories? How do we model them? So we model Zermelo-Fraenkel here, or we model them right in Grothendieck universe. Another issue is this, lambda calculus. Some of you, maybe like all of you, already heard Dana Scott Sunday, right? And there was also a talk like last year. So basically, there's a problem with lambda theory. It's pretty simple, right? Application and abstraction, we don't even need to actually introduce abstraction. We can have so-called applicative algebras. But the thing is, you cannot model it in sets, because we'll need to be able to apply everything to everything, meaning that we have to be able to represent our like universe as the power of itself. We cannot have it in sets. Yeah.
So the Lobbenheim-Skolem theorem says that every first-order theory that has a model has a countable model.
Yeah.
So why do we need these uncountable models?
That's kind of a different approach. Yeah. Well, see, it doesn't need an uncountable model, but see, you have you build a model, right? You build a model and you build it from outside, but inside it should satisfy this. So you like Lawvere, you build this, and the theory's own axioms. They are not satisfiable within the model. They're like visible from outside. That's how I see it. So like from outside here, you build that model, you build all these expressions. But these things are not features of the model itself, cannot be like built internally. But for lambda, for instance, we need to be able to have this, like every like element of lambda calculus is applicable to every other element, although maybe like there's no beta available. So Scott discovered a different universe, a different category where this lambda calculus can be modeled. Like the notation is d infinity, so it uses Scott topology, and this power is this the universe, not the set, right, consists of continuous functions from it to itself, and it's equivalent. I believe he was talking about this like Sunday. So, and there are slides for that. Well, yeah, and it's more like Leeuwenhoek's group, so allows us to model it. Yeah. Another alternative solution could be to take like a Cartesian closed category, almost any Cartesian closed category. This idea I found it in Barendirect in chapter 5. So, and take a topos, says to the power of that specific category, not just like category of all Cartesian closed, and interpret lambda expression in Kripke-Joyal semantics in that topos, and that would be also a solution. But again, I'm going to come up with a talk on this like Kripke-Joyal semantics next year, if I'm allowed. So these are the links. Bartosz basically all this like theory, this like simple explanation of theory is not from logical point of view, but from like theoretical point of view, is pretty much visible in Milevsky's what is it, a book just aside. So it was invented by Lawvere, and chapter 5 in Barendirect explains a lot of this. And we have this talk, and we have slides for Scott's talk for this year, like to get in. So basically the purpose of my talk was like dispel this idea that model and theory is the same. No. Models a theory, so have to disambiguate, and it helps a lot. Yeah, that's it. Thank you. Yeah.
So you said that if you have the theory and then you have the model, that if you prove it, and I was a little bit confused because you said something like, if you can prove it here or not prove it here, then that means it proves it there. Or so what's the relationship? Like,
well,
use the model to prove
I believe the relationship is like model is like a unit test, right? So if you can disprove something in a model, you'll see that it's wrong.
well, you can disprove it.
Disprove, yeah. But if you prove anything, well, see, there are like it's trickier. So there is a universal model. So but I'm not going there. So if you prove like stuff in universal model, it's probably the same as you prove it in the theory itself.
But if you prove it in the model, that's worthless. But you can disprove only.
Yeah. Well, that's how I see it. Like, have to look closer, but
depend on like the correctness and the sophistication of like the interpretation, and I mean, you have to assume that your interpretation was sufficiently constructed, right? Because that's a map that has to be, that doesn't come.
Yeah, it should satisfy all the axioms, right?
Right. Okay. I mean, it's a map that doesn't come for free, though. It doesn't seem trivial to construct an interpretation. So, I mean, how do you know your interpretation is correct? Just by satisfying the axioms?
Well, yeah, so how do we know that interpretation, that it's actually a model, right? So you have to prove that all these axioms are satisfied.
On like both sides?
No, on that side, on the theory side, like we may not know, like what we have to prove on the theory side is, are these axioms independent and are they like not contradicting each other? So, like how do they build, how do they prove continuum hypothesis independence? So they build once they build a model where that hypothesis is its negation, is valid, and the other one where it's the statement itself is valid, and prove that it's not contradictory. So meaning that we can have both models, meaning that the theory doesn't does not yield like whether it's true or false. So that's why we see that it's independent.
So the difference between interpretation and representation.
Again?
The difference between interpretation and representation.
I don't know what it is.
Okay. Well, you mentioned, representation of a theory in maybe another theory, right?
Yeah, so it's modeling.
Right. So, in the modeling environment, that's the same thing as interpretation. So, does interpretation have like a kind of functor-like kind of thing?
Yeah, it's actually a functor, but again, like probably like next year I'll try to show like how models can be represented
That's in semantics. So you don't have like interpretation, you don't have functors unless you're like going to semantics.
Yeah.
Oh.
Yeah, so like I didn't go into like category theory this time, and like probably well, actually it requires topuses. So given a theory, you build a topos on that, and so on. Yeah.
Are the slides for this talk available?
Oh yeah, slides. Here, lambda 18 TM many theories in model. We'll need to define binary operation. So in a monoidal category, yeah, we say, okay, that's how we model theories in a monoidal category, use tensor products. So we'll have like, I didn't see any source where people talk about this like in a strict way. But it's doable, of course. You just have to have like a proper interpretation. So it's not a topos where if you model a theory in a topos, you'll still have Cartesian products. But if you do it in a monoidal category, you'll have to talk about have something like this, and then like more issues show up, like how they call it, all this pentagram. It's in McLean's book. Coherence laws. So it's all tricky. Probably doable. Yes.
Yeah, what I was going to ask is, so you're saying that you could view semantics as just another theory, and then you're interpreting one theory?
As a theory where we interpret our stuff, where we model our stuff. Yeah. But again, like the problem could be that how do we model like these things? How do we model relations, right? Relational symbols. That's another thing, right? So.
Yeah. So, when we talk about, say, completeness, like semantic completeness of first order logic, well, I guess that's general. That's supposed to apply to any theory. I'm trying to see how all these different concepts relate to each other. I guess.
Well, yeah. So basically, if you talk about something within a theory, not involving like any models, right? So like not saying that like a group is a set. No, we can like build a lot of stuff in groups without involving any sets, right? So and use first order logic. Yeah, it's doable. But again, like see, if every time we talk about lambda calculus, sets are just not involved in discussion, right? You can do like, beta reduction, like abstraction, eta, alpha, without any mentioning of sets.
Right.
So it's like you don't need models for talking about lambdas, for instance.
I think I know this answer, but what is the value of using models?
Well, it's like mental values, so like disambiguate. So we know that it's not necessarily sets. Not everything is a set. A theory is a theory, and model is where like we model that stuff. So it's like a value of separating interface and implementation, probably. It's just
So the value so the value of models is that you can basically disprove or prove things.
Yeah. So what's the purpose of models? Like we talk about models all the time because, see, like. If you just start learning set theory, so the question is like, what's a set? And if somebody says a set is a notion from set theory, so people get totally like confused. That's not how they learn in school, right? In school they deal with objects, numbers are like whatever. So all these things kind of exist, right? But when we talk about theory, like nothing of that stuff exists. It exists only in our minds as like rules.
Okay.
With
So
no-
models are almost like the examples. It's the way that we
Well, yeah, they are, yeah,
describe this
yeah,
thing.
yeah, yeah.
Okay.